Okay, so this time we are going to look at a numerical example of SVM. So let's have a quick review from last time of the important formulas. Well, so first we have the Lagrange function that we simplify, and it is equal to summation of alpha I minus 1/2 summation I summation j. In here I and j, they're just index, okay? Alpha I, alpha j, yi, yj, xi transpose times xj, okay, and with the condition subject to alpha I is non-negative and summation of alpha I yi is equal to 0. We can call this as equation 1, for example. Okay. In addition, we have so first we need to solve for alpha I, okay, and then we can find the weight vector, which is summation of alpha I, yi, xi, and then we can solve for the bias. So this is the weight vector, and this is the bias, okay. So the dimension of the weight, depending on how many dimensions we look at. So the size of W represent, the size of the represent the dimension of the data points. But for the bias is scalar value. Okay, for the bias, we can compute it from any specific yk minus wk w transpose times xk. Okay, and in particular we only look at the support vector. Okay, so you can use any support vectors to compute this. In order to compute the alphas, you can because it is based on the data points that you look at, okay, you can specifically solve for equation 1 using only the support vectors, or you can use more data points besides the support vectors, okay. Then use alpha value to select which data point will be consider support vectors, right? But you don't want to use too many data points, otherwise the equation is going to be complex. Okay, so first this is the purpose of this lecture. We want to look at the we want to solve numerical example for all these above equations. Okay, so let's call this is equation 2 and this is equation 3. Okay, so let's consider this case where we look at a 2D problem. Okay, and let's say that there are two points that we will look at as support vectors. Okay, let's say that we have two data points. One is called x1, the other one is x2, okay. And so when we do training, we need the support vectors, and then we need the value of the class. Let's say y2 is 1 and y1 is -1. So this is the class, okay. And so that's it. Well, I mean, from this picture, if x1 and x2, they are support vectors, so let's call that x1 and x2 are support vectors in this case. Okay, well, it will be quite obvious that the boundary will be somewhere here. Okay, this will be boundary. Okay. And we know from last time that the weight vector is going to be perpendicular to the boundary, so it should be something in this direction. Okay, so it has to be perpendicular. Okay, okay, so let's take a look. So the goal here is, given x1 and x2, which are the support vectors, we want to find what are the alpha values. Okay, W, weight matrix, and then eventually the bias value. Okay, once we know the weight vector, once we know the bias, we can use these two as part of the classification rule. Okay, so let's look at equation number 1. Okay, so from equation 1, okay, we have the Lagrange function. Let me put just parentheses and dot, equal to summation of alpha I. Okay, in this case, because we only have two support vectors or two data points, two data vectors that we will use, so I is equal to 1 to 2, and minus 1/2 summation I is equal to 1 to 2, summation j is equal to 1 to 2. Okay, alpha I, alpha j, yi, yj, and xi transpose times xj. Okay, okay, so there are different cases we want to look at. Let us expand this. So we have alpha 1 plus alpha 2, and then minus 1/2. Okay, so first case we have I is equal to 1, j is equal to 1, so we have alpha 1 squared, y1 squared, x1 transpose times x1, and then plus alpha, the next case is I is equal to 1 and j is equal to 2, so we have alpha 1 alpha 2, y1 y2, x1 transpose, x2 transpose, x times x2, and then plus alpha 2 alpha 1, x2 transpose x1, and then plus the last case where I and j are equal to 2, we have alpha 2 squared, y2 squared, x2 transpose times x2. Okay, so let me write on the side that here we have 4 cases. I is equal to 1, j is equal to 2. This is, oh sorry, so first case I and j are equal to 1, and then second case I is equal to 1, j is equal to 2, then I is equal to 2, j is equal to 1, and lastly I and j are equal to 2. Okay, so if we use the vectors that are given above, so what we will have, so let's compute on the side. Okay, So we need to find x1 transpose times x1, right? And from above, x1 is minus 1 2, okay, because transpose it becomes column vectors, and times x1, which is minus 1 2, okay. So in essence, x1 transpose times x1 is actually just the magnitude of x1 vector squared, okay. So just multiply it, so we get minus 1 squared plus 2 squared, okay, so we get 5. Similarly, we also need, so this is x1 transpose times x1, we also need x2 transpose times x2, okay, x2 I think is 1 2 times 1 2, okay. You can use the same approach, you get 1 squared plus 2 squared, you get 5. And next we also need x1 transpose times x2 or x2 transpose times x1. These two are actually equal, so x1 transpose times x2, so this will be minus 1 2 times 1 2, okay. The difference is minus 1 and 1, okay. So we'll have minus 1 times 1, which is minus 1, and then plus 2 square, which is 4, so we have 3, okay. So this will be the same as x2 transpose times x1 as well, okay. Additionally, we also need to find y1 squared, okay. Y1 squared is just minus 1 square, which is 1. Y2 square, which is 1 square, is also 1. And then we have y1 y2 or y2 y1, it is going to be minus 1 times 1, which is minus 1, okay. So once we have this, we can plug it back into this equation. Let me call this equation 4, okay. Additionally, you notice that this term and this term, I think I forget something here. Alpha 2 alpha 1 times y2 y1, okay. So you notice that these two terms, you know, this term and this term, they are the same, they are equals, so we have twice of the value, okay. So we can just plug it in, so we'll have this is equal to alpha 1 plus alpha 2 minus 1/2, okay. And first term, we have 5 times alpha 1 square times y1 square, which is 1. So we have 5 alpha 1 squared, okay. Next term, which is the middle term. So for the middle term, we have twice of the value, right? So I can put 2 alpha 1 alpha 2 times y1 y2, and then x1 transpose times x2, I get 3, okay. And the last term, I also have 5 alpha 2 squared, okay. So if we simplify it, we will have alpha 1 plus alpha 2 minus 1/2 5 alpha 1 squared, and the middle term, we have minus 1 here, so it's minus 6 alpha 1 alpha 2, and then plus 5 alpha 2 squared, okay. So you notice that here the Lagrange function is a function of alpha, okay. So alpha 1 and alpha 2, they are the unknowns that we have to solve, Okay, and then we can solve the W matrix and bias later. Okay, let's call this as equation 5. Okay, so what do we do? Well, we want to optimize the Lagrange function. So in order to find this, we will need to differentiate the Lagrange function with alpha 1 and alpha 2. Okay, and if we do this, what do we get? So for the first term in the parentheses, we have alpha 1 plus alpha 2. If you differentiate with alpha 1, we just get 1. Okay. For the alpha 2, when we differentiate with alpha 1, we get nothing because there's no alpha 1 in it. And then minus 1/2. And then first term, differentiate 5 alpha 1 square. What do you get? Okay, we get 10 alpha 1 minus second term. We only have alpha 2 left, which is minus 6 alpha 2. And then for the last term, which is 5 alpha 2 squared, we don't have nothing when we differentiate with respect to alpha 1. So this is all we have. Okay, and when you optimize, maximize or minimize the Lagrange function, you differentiate and set it to 0. Okay, and we will find what it is. Before we do this, okay, let's keep it here. Let me call this equation 6. Okay, in this case, because there only have there are only two variables to solve. Okay, so rather than differentiating with alpha 2 as well, so I'm going to use another property from equation number, let me see, I'm going to use another property from equation number 3, which is here. Okay, oh sorry, no, not number 3. I'm going to use this equation. Yeah, so this condition, you know, will give you relationship between alpha values as well. Okay, so from summation of alpha I yi equal to 0, here I is equal to 1 to 2. So you have alpha 1 times y1, which is minus 1, plus alpha 2 times y2, which is 1, equal to 0. Okay, so if you solve this, you will get that alpha 1 is equal to alpha 2. Okay, so this is equation 7. Okay, so we can say that from equation 7, equation 6 becomes, so basically we will replace alpha 2 in equation 6 with alpha 1. So we have 1 minus 1/2 times 10 alpha 1 minus 6. Instead of writing alpha 2, I write alpha 1. This is equal to 0. Okay, so it means that we have two variables, and here we also have two equations to solve, which is equation 6 and equation 7. Okay, if you have more alphas, like alpha 1, alpha 2, alpha 3, for example, then you need to differentiate 2 times with alpha 1 and then alpha 2 to get 2 equations. Then you can use this condition to get the third equation to solve 3 variables. Okay, so here to solve this, we have 1 minus 1/2 times 10 minus 6, you get 4 alpha 1. This is equal to 0. Okay, I can multiply 2 on both sides, then I get 2 minus 4 alpha 1 equal to 0. Okay, so therefore alpha 1 is just 2/4 or 1/2. Okay, and from 7 we get that alpha 2 is also 1/2 as well. Okay, because alpha 1 and alpha 2 are equal. Okay. Okay, so that's what we have for alpha values. Like I mentioned, you can solve with more equations if you have more alphas to solve for. Okay. Okay, so then from here, what do we do next? Because we want to find the weight vectors, right? So then we find the weight vectors from equation number, equation number 2. Yes, from equation number 2, and bias from equation number 3. So we find W matrix from equation number 2. Okay, W is equal to summation of alpha I, yi, and then xi, where I is equal to 1 to 2 as well. So this is alpha 1, y1, x1, plus alpha 2, y2, and then x2. Okay, and okay, so we just replaced what we have. Alpha 1 is just 1/2, y1 is -1, x1 is the first support vector, which is -1, 2, and then plus alpha 2 is also 1/2 times y2, which is 1, and x2 is 1, 2. Okay, so if you sum this together, what you will get is something like this. You get 1, 0 out of this. Okay, so this is the 1, 0 as the weight vector. And if you look back in the problem that we looked at earlier, okay, so you see that this W is equal to 1, 0. Okay, 1, 0 is right here. Okay, or maybe I write as the triangle. So this is the weight vectors, okay, which is perpendicular to the boundary. And next we need to find the bias, so we use equation 3. Okay, so from equation 3 we have the bias. The bias can be computed from any support vector. So let's say that in this case we use the support vector 2. So we have y2 minus w transpose times x2. Okay, this thing from last time, it was written as the inner product of W matrix and x2. Also, it could be written as the W vector and x2 in vector form as well. Okay. So y2 is what? 1 minus the weight vector transpose is 1, 0, and times 1, 2. Okay, so we have 1 minus 1. Okay, so therefore we have the bias is equal to 2. Okay, oh, it's equal to 0. I'm sorry. And if instead of using x2 you use x1, you will get the same bias anyway. Okay. Okay, so for this example, so okay, therefore we have W vector as 1, 0, and the bias in this case is simply 0. Okay, so for the classification rule, after the training of the SVM, what we have classification rule like this. Okay, so the classification rule goes like this. So given any data points that you want to classify, okay, let's call it any data point, let's call xp. Okay, so okay, the SVM will classify xp to either +1 or -1. Okay, it's gonna be -1 or 1. Okay, by computing whether W weight matrix that we develop multiply with xp. If it's less than or equal to -1, then we assign it to class -1. If W matrix that we W vector that we developed, that we computed, transpose multiply with xp, if it's greater than or equal to 1, then we classify it to class 1. Okay. And let me give a short note here, or let me also put parentheses over here, put the bracket over the box over the solution. So this is like the answer. Okay, so during that, so let me put a note here. Okay, so during training, okay, we obtain W matrix, a W vector, and also bias. Okay, and then during classification or prediction, I think it should be called classification. Okay, then we have the classification rule. Okay, cool. This is note number 1. Note number 2. During the training, data points can be put in the equation. Okay, but only those with alpha I greater than or equal to 0 actually not 0, should be greater than 0. Okay, will be used as support vector. Okay, so for any data points that you get from the solution, you get alpha to be 0. When you compute the weight, it doesn't add to any values in there anyway. So only the data points that you put in the equation and you get the alpha value that are greater than 0, then they will be used as support vectors. Okay. Also, additionally, I want to add that in order to find the alpha values above, we can use some software like Python or MATLAB as well to optimize this. For example, if we look at MATLAB, for example, okay, in MATLAB they have the optimization solver, and the command is called elf solver, meaning that it solves equations. Okay, and in this case what you need to do is first you need to write a function, whatever names you want. Let's say I put the name as Lagrange function. Okay, so this function has to be written like this. So this is the format of function in MATLAB. Okay, and with the input of, let me call as A. Okay, where what is A? A in this case is the alpha we use. If in this case we used alpha as alpha 1 and alpha 2, this A has two elements, alpha 1 and alpha 2. And then we need to write two functions or two conditions for alpha in order to solve it. Function number one is written as to represent the first equation from our derivative. Okay, so if you go up here, the first function, the first line in the function, we are going to write it as equation number 6. Actually, equation number 6, or I can write it as yeah, I can write as equation number 6. Yes. So that's the first line in the function that I will write in MATLAB function. And the second line, I will use the second condition, which is in this case, this one. So the second condition is minus alpha 1 plus alpha 2 equal to 0. Okay. So the way to input the condition in this type of MATLAB function is to write both conditions with 0 on the right hand side. Okay. So when we go to MATLAB, we will write it like this. So we will write it like this. So F1 is going to be 2 minus 10 times alpha 1. But in this case, alpha 1 is A1. Okay. And then plus 6 times alpha 2. In this case, is A2. And then for the second line, here we only have two variables, alpha 1 and alpha 2, so we only need two lines of the functions or conditions. So second line is the one which is minus alpha 1, but in this case is A1, and then plus alpha 2, which is A2, okay, and that's all. And then you end the function here, okay. So when you go to the command window in MATLAB, that you're in the same folder as this function, first what you do is you need to write the initial condition. You can set it to be anything. Let me put it 1 1 for example, and then you set the function to the Lagrange function that we built. So we just set up a variable called fun. You can set anything that for this variable, for this unknown vector. Okay, we solve the Lagrange function. Okay, and then we use the fsolve command with the input of the function on the previous line and the initial condition, which is A0. Oh, sorry, it should be A0, not X0. Yes. Yeah, that's all. And then, you obtain, once you enter the command, you get something like A is equal to 0.5 and 0.5, which is in this case is 1/2 and 1/2 anyway. Okay. You can modify this to solve the optimization, any optimization problem. Okay, but you just need to modify the function with the variable that you want to look at. This is useful if you have many alphas, like 10, 20 alphas. You don't want to solve it, you can just use this optimization. But optimization in MATLAB, there are many variants. Okay, so if you're interested, please take a look at it.